ratio of V out into R of divided by R and negative, because this is inverting. So this is your output voltage. So this is so easy. You don't need to bother about the transistors, biasing, all this complication. This is simply you're getting the amplifier output voltage, and you can select whatever your gain you need. So gain is nothing but your RF divided by R1, the ratio of two resistance. So it's very simple. You just need to buy two resistance and fix, and you'll get the output voltage. So easy. There's no need of a capacitance, all those things. Although the cost of the IC is also very less, as around 5 rupees, so less than that. And so this is the advantage of Opamp. So most designers unlock people design works on the Opamp. Very less people work on the BJT level or MOSFET level. But this is required if you are designing an IC for a company or some you're designing a gadget. You need to have an IC, because Opamp also comes in IC, like 1, 2, 3, 4, 8 pin IC. So this is for low cost. So if you are designing a IC for your company, they also have to design a chip for that. Then you have to design using MOSFET and the transistors. Or you're designing something for your household purpose. You're designing a water level controller, a toy, or a robot or something. Then you can use the transfer level designs, right? So otherwise, transfer level designs are not used in industry. They'll directly go for the chip fabrication. But the chip is very high initial investment. You need to have spent at least 5 lakhs for the chip, and you will get around thousands or 5,000 chips, and you have to use it. So there are some disadvantages of chip fabrication, but now but it has its advantages. What is the advantage of chip? In a low power, we can design using low power techniques. We can customize our application for our own need, on device, customize, and power and frequency can also be power can frequency can be maximize the speed, right? Because we are designing only what we need. So that is advantage of IC design. IC. So this is advanced course, analog IC design. Analog IC. This is another course in digital design or VLSI. Digital IC design is another course which you may learn in 7th. Okay, so that about the course. And now we'll discuss about the non-inverting amplifier. So this we discuss inverting amplifier. Now we'll discuss non-inverting amplifier. So in non-inverting amplifier, we give the input to the non-inverting plus terminal, right? And what about the minus terminal? We have to ground it with a resistance, some resistance like this. Now, what are the feedback? Yeah, here also there is a feedback. There is some feedback. So this is R2, this is R1, and this is V output. Right now, using the virtual ground principle, can you calculate the output voltage? The answer is yes. It is pretty simple. So only few algebra required. So this is some voltage here, and this is some voltage here. The virtual ground principle, this is nothing but this voltage are same, right? So this is nothing but V in is coming here also, right? Now what we'll do? Now we need to assume a current here. So we need to assume a current. For example, I1 is passing through R1, and this is maybe coming from here. So this is I2, right? So we know I1 equal to V divided by R1. Okay, and I2 V out minus V in divided by R2. Right, because it is pushing. So, and we also know what we also know, I1 equal to I2. This also we know, right? Why? Because the input impedance is input impedance of the infinity. Input impedance of the op-amp infinity. So there is no current going inside the op-amp because input impedance infinity. So this assumption, all the things happens using the feedback principle, right? So I1 equal to I2. This is very easy because input impedance is infinity. Input impedance is infinity. And I1 equal to V in by R1. And so we can equate this to, because of this I1 equal to I2. So we can say, so this implies V in divided by R1 equal to V out minus V in divided by R2. Now what happens? Can you simplify this? Say V in common, 1 plus R1 plus 1 plus R2 equal to V out, something like this. Yeah, R2 is there. Here R2 is there. So what happens? So V out divided by V in. What happens? V out by V in. This is the gain. This is what we are interested in. V out divided by V in. That means R2 divided by R1 plus 1. Right? So this is what we get. This is the gain after simplifying. So gain of a non-inverting amplifier is, there is no negative sign, 1 plus R of divide or R2. Here is R2. 1 plus R2 divided by 1 plus R2 plus R2 divided by R1. 1 plus R2 divided by R1. Okay. So this is non-inverting amplifier. So gain. So you can easily see at high gain, we can one can be disregarded, and we can, if R2 by R1 is very high, R2 by R1 is very high value, much greater than 1, we can say gain approximately can be equal to R2 by R1 also. Okay, but you should know this expression. This is most important. Okay, so this is about non-inverting amplifier. Non-inverting amplifier. Yeah, just seen this non-inverting amplifier. Now let's see some other application. For example, if you need to average of two voltages or three, let's say three voltages, have V1, V2, V3. So what we'll do? We need to average. So what we'll do? We'll just connect these things, and we give this as the input of this op-amp. Say for example. So now I'm going to find the averaging circuit. So we have three inputs. We need to take the average. Now let's give it to an op-amp. I'm selecting a inverting configuration and ground it. This is my Vout. Okay. Now this is my RF. Now let's see what is the output voltage if you are giving three. Say this is V1 is going through R1, V2 is going to R2, V3 going to R3. So in this case, what we do is you can use superposition principle. So all this analysis is done. We have multiple voltage sources in the input. You can just use the superposition principles. That means we can assume V2 is not there, V3 is not there, and calculate output using V1 only. So we have the circuit, so we can just calculate the output. Output will be what? Output will be V input into RF divided by R1, right? Then we take the next. Then we take the next output. This is VO1. Now VO2 with only two elements. So V2 into RF divided by, yeah, definitely there's a negative. There's a negative sign. Now V3 is VO3 equal to minus V3 into RF divided by R1, because this is non-inverting amplifier. Now the total, according to superposition, the total Vout equal nothing but VO1 plus VO2 plus VO3, right? So we just can see. So we can just see is nothing but, you can see this nothing but V1, yeah, V1 negative, I'll take common V1 divided by R of divided by R1, or I can take it common R by R1, R1, R2, R3. It cannot be taken. Okay, okay. So this one difference here, R1, this is R2, this is R3. Yeah, now it is fine. Okay, now we can see here, if I take R1, RF and R1 all in the ratio, RF divided by R1 equal to 3 is to 1 or 1 is to 3. I can say 1 is to 3. 1 is to, this is up to designer, no? What ratio I need to take. RF by R1 is 1 is to 3. And same is RF divided by R2 is also 1 is to 3. Same as RF by R3 is also 1 is to 3 or 1 by 3. So this becomes 1 by 3. So this becomes also 1 by 3. This becomes also 1 by 3. So what happens? Now we can see the output voltage is so the output voltage is minus negative sign is the V1 plus V2 plus V3 into 1 by 3, that is divided by 3, right? And this is my output. So what I'm doing, I'm taking the average of V1, V2, V3, right? How I'm doing? Because I just need to manipulate. I just need to, yes, manipulate the value of RF and R1. That's it. So I'm taking average. If I have two input only, for example, I don't have V3, I can make RF by R1, R1 equal to 1 by 2, and R of by R2 is also 1 by 2. Then I'll get, instead of this, I'll get divided by 2. So I'll get an average in this case. But negative sign definitely remains there. So in order to remove that negative sign, for example, we have taking average of two voltages, that is V1 and V2. To remove that negative voltage, what we can do? This is minus, this is plus. So it's, for example, you're taking average here. So this should be, if this is R, if this is R, I'll take this one. How much should be this R of, this is RF. If this is RF, RF divided by R1 should be equal to 1 by 2. So this I need R by 2 for working as a averager of two voltage. This RF equal to R divided by 2 I need. Okay, because this is R, this is R. Okay, this is R by 2. Now output voltage I'll get how much? V output equal to V1 plus V2 divided by 2. A negative will be done. So now to reduce this, to equalize this negative voltage, what we do? Again, we will add one more. We'll add one more non-inverting amplifier. One more inverting amplifier. So the negative is cancelled, right? So I'll add one more inverting amplifier. Now here, what is specialty? Here I can both are as to be same value. This R Rx equal to Rx. Very fine. Now what happened? The output is the minus is changed because the gain is minus feedback resistance divided by series resistance. But here both are same. Rx Rx plus minus 1. So the gain is minus 1. So this is called there is no, this just need gain is 1 and my gain is 1. I'm just changing the polarity of the output. So I got the output is V1 plus V2 divided by 2. It's called input follower. Input for this, whatever the input is just following something. I'm not sure this. Okay, so what do you see? We have a non-inverting configuration and we can take the average or whatever is processing we can, and then we need to again connect to a non-inverting stage again. So minus into minus 1 is plus. So this is, we can reverse the polarity again. Okay, so that's all about, then we can have some filters also using this op-amp. So, we have discussed one kind of filter. One kind of filter is this. This is the resistance and the capacitance. So if this is, you can say the capacitance act as a short circuit to AC or high frequency, right? So in the input, if the input, there is some high frequency signals here, this high frequency will be short circuited across the capacitance C, right? The high frequency will be short circuited across the capacitance C. So this V out will not be the, no high frequency will then be V out. But the low frequency is there, that will be definitely V out. For example, we have signal like this. We have AC signal with some high frequency pulses, something like this. This is my input. So we can see high. What are the high frequency part of this input? What are the high frequency part of the time? We can see the high frequency parts are, these are the high frequency parts. So this is the high frequency noises, interferences or some kind of noises is happening. So all those high frequencies will be short circuited across the capacitor. So my output will be something like this, filtered wave, something like this. Something like this, because all the high frequency short circuit across the capacitor. So the same concept, Opamp HPF, low pass filter. This is a low pass filter. We can see this low pass filter because high frequency short circuit across the capacitors. This is this low pass filter output, LPF output. So this is conceptually right, but if we had Opamp, this works much better. So now design this, what we'll do? We can use a resistant and a feedback capacitance. So this we can give input here. So this acts as a low pass filter using Opamp. Okay, we have done nothing. We are just executed. We have just implemented the same thing which we are conceptual. We know this is a low pass filter. So 1 minute. Okay. I hope I'm audible. So this is a circuit of the low pass filter. So let's see a circuit of a high pass filter. The conceptual concepts remain the same. Now high pass filter, we need to eliminate all the high frequencies. So this capacitor will eliminate all the high frequencies and we need a resistance. So this is the V output. This is V input. So this is R, this is C. Right? Now how this happen? How this works? Uh, yeah, we have a high. For example, we have some waves like this input, which has some high frequency or low frequency. So we can see this high frequency part here. These are the high frequency vehicle in the waveform. These are the high frequency vehicles. So all this high frequency will be allowed to pass through the capacitor, and the low frequency will not be passed to the capacitor, right? Because we should explain capacitor impedance X is equal to 1 by C omega. So right, so the for the frequency high frequency, the impedance will be uh, so high frequency impedance will be very less, and low frequency impedance will be very high. Okay, so this is the concept. So output will be something like this. We will get the low frequency part only. So this is called a sorry. This is high pass filter. So I'll get high output in the output. So we'll get something like this. Something like this in the output. Right. So this is we are getting high frequency signals in the output. So this is a high pass filter. High pass filter. The same thing can be implemented using Opamp. So we can just connect the Opamp minus plus ground this in the capacitor first, then we'll have a resistance second. Right. This is V out. So the main question is the high pass and low pass. What are the factors which decides the which frequency I'm getting pass, which frequency I'm getting attenuation, and all those things. The value of R and C decides. Okay, you know about the basics of filters. That means if this is a filter, if my gain is this, the frequency is this is a low pass filter because the low frequency is allowed to pass this low pass filter. If it is only this is a high pass filter, and if I'm allowing the frequency in this range, it is a band pass filter. Band pass filter. So the low pass filter is high pass filter. So we should know gain versus frequency curve. Okay, I think that much is sufficient for the op-amp part, and all the things will be basics, and you can understand. And then I just want to cover some concept like maybe I'll cover some concepts of yeah, small signal. That's something which small signal and large signal. Small signal versus large signal versus large signal. Okay. So what is this small signal versus large signal? So the small signal models are those models which we basically use for AC analysis. AC analysis. AC analysis. AC analysis. What about the large signal analysis? We were explaining the DC biasing, stability of bias with respect to output Kara load line. So that kind of analysis is called large signal analysis. We can say DC analysis and large AC voltage, how the reaction or the response of the circuit for large voltages and AC voltages, large signal analysis. Large signal analysis. Okay, so that's the difference. In small signal analysis, we focus on the minute variation in the input signal. That means slight AC, I'm giving slight wiggling of your base emitter voltage, and what is the response, how much gain is getting. And large signal is basically of biasing, high voltage changes, and DC biasing, high AC signals, etc. So that you should know. Now, there is a slide model. This is a modeling in the transistor, which we didn't discuss, but it is important. No, not for right now. Maybe if you're for higher studies, or if you're doing a course on digital IC design, analog IC design, especially analog IC design, we need this modeling. So usually, the small signal model is something like this. Uh, we have something how we do small signal modeling. This is one example. This is an example of a BJT, small signal model of a BJT. So what are the important things here? This is a base, this is the emitter, and this is collector. So what this implies this, we have the three-terminal transistor. The three-terminal transistor may be very difficult to analyze for a common man or a student which is who understands only basic electrical or electronics. But in order to model the transistor using a resistance, current source, and voltage source, and ground, and all those things, it is much simpler to visualize the transistor, see the working of the transistor. So this is done using models, small signal models or large signal models. This is small signal models. Small signal models. Okay. So here the only thing is interested in what is the behavior, how the behavior of the transistor is modeled using this model. So this is V input. For example, this is V input, right? And this emitter, I'm just grounding the emitter. So this is a common emitter configuration. You can say common emitter is common. Emitter is common. This is emitter. This is emitter. Common emitter configuration. Configuration. And this is V input, and the V output I will take from here. Now, what is this current source doing? This current source is actually an approximation of the transistor working. So this concentration value IC, this is IC equal to beta times IB, beta times IB, and this is IB here. Okay, so this is a simple model of a transistor. So what is meaning of this model? Even if whatever the current is passing, IB is passing through RP or the base to emitter, and it is magnified. Is magnified how much times? Beta times into IB. I'll get this in IC in the output of the transistor, collector transistor, and this can be exhibited, or this can be given in the output of my transistor. So this resistance also in order to model the early voltage. What is the early voltage we discussed? Instead of current source, there is although ideally it should be current source, but there is slight change in the current. That's called early voltage, right? So this R0 is modeled the that early voltage change in the voltage also. So this is modeled using the R0 resistance. So this is V out is across the R0. Okay, so that much once again explain. In order to explain the complicated three-terminal device or transistor or amplifier, we make a small signal or a simplified model like this, a resistance and all the simple current source, all things which we know, and we'll just write behavior of the transistor here, or the beta times IB, where beta is the input current, which is input voltage VI or VB here, and this is the IC fine, and this V output is taking across the output. So this is simplified model of the transistor, right? So this is, for example, this is grounded, this is emitter terminal, this is base terminal, this is collector terminal. right? So this is the current source and all those things. Okay, so this is called some modeling, and even the BG or MOSFET also can be modeled like this. So you should understand what is basic things of what is happening, this modeling. So that's it. That's my only idea. Okay, so for example, MOSFET, we can do the same thing. Input, there's a voltage, VGS, and here, MOSFET, we know this gate is open circuit, resistance is infinity. So VGS I'll take like this, and the output is current only. So this is voltage control current source. This is voltage control current source. So this is, can say this is source, this is gate, this is drain, right? So what is this VGS? So this is nothing but some current ID. So here ID is represented using a voltage controlled current source. So we can say VGS into we can say VGS into GM into VGS. So what is GM? GM, we have discussed the transconductance. So transconductance, we know what is trans, input output. So this is something output. So trans, the GM is transconductance. Conductance means one by resistance. That means current by voltage. Say current by voltage, and trans means input by output or output by input. So that is here the input is VGS. That means input is VGS, and what is output is IDS. So this is GM, IDS by VGS. So this is the transconductance separately. Output is taken across this point. So this is, I'm just explaining what is the small signal model. Or this is in MOSFET, or even the JFET is also will be similar, because we know the input impedance is infinity here, and here also there can be a early effect here, R0, you can put R0 also, right? So here also, although we assume this is current source, same current, but in practicality there is slight increase in the ID versus VDS. So this is called early effect in terms of BJT or also. Okay, so now this modeling is okay. Although you may get this questions when it is a theoretical exam, but in objective exam is limited. But you may get, but you should just know what is this model. Every transistor, BJT, MOSFET, or JFET have this kind of modeling. Now one more important thing we want to discuss is, yes, yeah, there are different kinds of feedback. Feedback can be positive feedback or negative feedback. So what is feedback? Say I have an amplifier here, output is, this is V input, V output. So what is gain? AV stands for gain, or I can say A, simply A. So gain is nothing but output divided by input. So this is without feedback. Suppose I am connecting a feedback. I am connecting the output to the input. Maybe there is some processing also, some processing, some beta, can be whatever, and I'm giving to the input. So for example, this is an adder here and adder here. So what happens? My feedback is adding to the input. So this is called positive feedback. Clear? If my input is adding to the my feedback is adding to the input voltage, it is called a positive feedback, because this is plus, this is plus. Now next input is greater. Now input V1 is going to be greater because the input has been added, right? So that is called positive feedback. What about negative feedback? If this plus sign is converted into minus sign, we'll have a negative feedback. Okay, so if you say, for example, this, what is this voltage here? This is V output into beta, because beta is been multiplied. This is system model, transfer function beta. So V output into beta. So what is in positive feedback? New input is V in equal to V1, sorry, V1, which is input to the amplifier, V1. This is the V1. V1 equal to V in plus V output into beta. Okay. So likewise, if we substitute, we get the transfer function of a feedback amplifier V output divided by V input is nothing but the gain A divided by 1 plus or minus A beta. This something will derive. This is the transfer function of feedback amplifier. And where the plus comes for negative feedback, minus comes for positive feedback. Okay, so this I'll just explain here. Here, so the gain of a positive feedback amplifier, gain of a negative feedback amplifier, A divided by 1 minus A into beta, right? Equal to negative feedback A plus 1 plus A into beta. So this is a positive amplifier gain. This is negative amplifier, negative feedback amplifier gain. Positive feedback, negative feedback. Right. So what is the most important thing you have to note here is the denominator. You can see the gain is much in positive feedback gain. The gain in a positive feedback is much greater than 1 because the denominator is much lesser. And what about the negative feedback? You can see the gain is not much. Gain is not much. Gain is, you can see it's much less. Gain is much less, although it's not greater, right? So you can say in negative feedback, the gain is transformed. The gain is utilized for increasing the stability and reducing distortion and etc. and increasing the swing, bandwidth, etc. In positive feedback, the gain is very high. So we can see if you see the output graph, if you give some small sine wave, you can see that if you are giving positive feedback, what is going to happen? This is slight wiggling and is going to increase the output like this. So this is very unstable. Can we go to unstable stage? So this is not recommended always. What about negative feedback? You can see slowly, whatever we input is slowly coming to the zero. So this is negative feedback. Now, ideally, if we need sustained oscillation, which is constant oscillations, constant amplitude oscillations, what we need, there is two conditions, which is called Barhausen criteria, that you should just note it down. Barhausen criteria, this means A beta, the denominator should be A beta equal to 1. The magnitude of A beta should be equal to 1. That is this guy, this denominator guy should be equal to 1. And the angle phase difference which I'm giving to my input signal also should be 0 degree. No phase difference should I give, so that I'll get a sustained oscillation. So this is the principle of oscillator. In oscillator, we don't need to give input also, even if we give 0 input, because of thermal voltage, it gets having a positive feedback and it gets on and it's amplified till it gets a stable box. So where the use of oscillator? This oscillator is used in almost all the digital circuits for clocking. We may get clock square pulses, but these square pulses are made using sine pulses or sine waves only. So oscillator, they can be analog. Mostly it is analog. We have crystal oscillator in digital circuits, right? We have RC oscillator, LC oscillator, crystal oscillator, etc. These are sinusoidal oscillator. So in this is the Barhausen criteria. Barhausen. So what are this thing? AB, magnitude of AB equal to 1 and angle divided by AB should be equal to 0. Okay, so that about the basics of oscillator. What are different types of oscillator? Sine wave oscillator, square wave oscillator. So sine wave oscillator can be designed using RC oscillator, LC, and crystal oscillator. I think you might have seen in some of your gadgets. Crystal oscillator is some gadget with the 2 pins like this. You can see something like this. Something it comes like this also. Crystal oscillator. There's a metal outer covering, and what it gives, it just some crystal is there, some chemical crystal is there, or piezoelectric crystal is there. Whenever you apply a DC voltage, what it gives, it just start vibrating. and it gives some as a wave, sine wave. So this is kind of peculiar property of a some device. So based on that input application of DC input voltage, it start vibrating and gives a constraint oscillation, or we can get oscillation. So this is called basically principle of oscillator. Okay, so oscillator, the two criteria, bar oscillating criteria is AB, magnitude AB should be 1, and angle AB equal to 0 degree. So this is just for understanding theoretical purposes. This is the condition where this is applied to feedback system A beta. This is the gain, feedback gain. This is the feedback gain, right? Where plus for negative feedback and minus for positive feedback. Okay, that much about the mm, so one more concept, if you're understood, I can just for briefly, I can just discuss there's a concept about current mirror. So I'll just explain what is current mirror. That's it. Okay. So in IC, if in IC you need a lot of, for example, designing an IC, there are a lot of places where you need constant current. For example, we have already know there's an operating point of a transistor where the load line, we have something like this. Now this is a load line, and this is your output characteristic. So this is your operating point. So this I need a fixed IC and a VCE. If this current is going to change, my operating point is going to change, which I don't want. I don't want my operating point to go up and down, because this results in clipping of my output waveform and my signal is lost. So I don't want this change in IC. But in IC, there are a lot of amplifiers, there are a lot of biasing. So I need my lot of IC in this part, IC in this part of the circuit, IC in this part. All the ICs should be same. So we use a concept of current mirror. What is the concept of current mirror? We are trying to mirror the current on different amplifiers or different parts of the circuit. That is the concept of current mirror. So basically, current mirror is nothing but we have a BJT, we have a diode connected. What is diode connected? With the collector and base is shorted together, it is called diode connected BJT. Right? And to the collector side, we collect a current source, VC. So this base voltage, this base emitter base voltage, if I give to different transistors, same, I can short circuit to all different transistors in the circuit, I'll get the same current in them, all of their branches, IC. Right? This is IC, this is constant current, and this current is producing voltage, base emitter voltage here. If I connect this base emitter voltage to all the different transistors in my circuit or chip or in my silicon, I'll get the same IC in all other branches. So this is called mirroring. This is called mirroring. Mirroring. What is I'm mirroring? Mirroring the current IC. The basic thing in this is, we know that IC equation, we know IC is equal to I saturation. This is diode equation. We're discussing diode. That is exponential VB divided by VT, something like this. Yeah. Here we know VB is constant, I is constant, VT is constant. So we can say IC is constant if this is we fixed VB, we got fixed IC. So this is the concept I'm using in the current mirror. So what is the concept? I'll repeat again. If I'm fixing my VB in one transistor, that transistor will be a fixed IC, then I'm going to mirror that VB in all the places where I need that kind of IC, exactly that magnitude of IC, I can mirror, giving that VB, same VB will be here, same VB will be here, same VB will be here. So what happens? Because the fixed VB, my IC is also fixed. So this IC I'll get fixed in the output. IC here, IC is also fixed. So this is called current mirror. Current mirror. I'm mirroring the current in different branches of the circuit or different branches of the IC or different transistor circuits. So this is called current mirror. Right? So current mirror starting, I need a diode follower. What is diode follower? I have a transistor like this, base and collector is shorted. So Okay, so this BV base emitter voltage, I'm going to mirror to different parts of my circuit. So this IC, which I standard IC, which are designed in one part of my circuit, IC current source, can be mirrored in different part of the circuit any number of times I need. So this is called current mirroring. So that's the concept we should understand. In ICs, we need constant IC or constant current because I need to keep my word operating point fixed. IC should be fixed. So I'll keep my to fix my biasing or IC fixed. I'll design a initial circuit its current source IC, and I'll collect that voltage, base emitter voltage of that circuit and mirror across all the different transistors. Now all the transistors will get same base emitter voltage, and then they'll also get the same IC. So the equation I'm using is IC is a function of IS saturation current e raised to VBE divided by V thermal voltage. So here all the things are constant. IS is constant, VT is constant. Only thing is VBE. So VB is a function of my IC. Okay. So that is why I'm connecting here diode connection. What is diode connection? Because of this equation, I'm using my diode connected transistor. So base and collector is short circuit. Okay, so that is called diode connected. So because of this property of a diode, actually we are using transistor as a diode only here. Because of this property of diode, I'm connecting the collector and base of the transistor to make it as a diode. So this is equivalent of a diode only. Okay, fine. So this is the property I'm using because of this equation, the diode equation only, right? So just mirroring the same magnitude of current in different parts of the circuit or the chip. That's called mirroring, current mirror. Same thing I can do in MOS also. MOS also I can use a MOSFET and do the same thing. So there is works there also. Okay, so that's the basic concept you should know about the current mirroring. And in your course, we cannot complete all those things because you had not done the basic electronics course in the first year. I hope so. So we cannot jump into the all those mirror and different types of amplifiers because this will be too hectic for you, especially in the online quiz. So if you're taking a basic course in the first year, basic electronics, then we can easily go to this amplifier configuration, small signal, current mirror, and all those things. But in this your case, you can only this much is sufficient. You should know what is basics, what is current mirror. We are mirroring the current using some diode connected transistor in this initial. And what is the oscillator? Oscillator is a feedback. Using the concept of feedback, we are we are using Barkhausen criteria. AB magnitude equal to 1, AB angle equal to 0 degree, phase I'm giving 0 degree. Then I'll get a feedback and I'll get a sustained oscillation. That is called oscillator. The different kinds of oscillator, LC, RC, crystal oscillator, and in digitally also we can make some square pulses using a 555 timer ICs kind of thing. Okay, there are applications part. And different types of modeling is a small signal modeling, large signal modeling, and different types of transistors, BJT, MOSFET, JFET, and Opamp applications, Opamp properties, characteristics, and diode properties, characteristics, ideal diode, non-ideal diode, all those things. Okay, and that much is sufficient. Um, and one more thing is sufficient, which I'll share in the Google Classroom. That means different properties of amplifier. I think that will be sufficient. Different properties in the sense common base amplifier has low input impedance and high output impedance, and what of the gain. So this thing comparison between common emitter, common base, and common collector. That's much is sufficient. And common collector is also called as voltage follower because the gain is very less, right? Output impedance is also very high. So that all things, these three comparison I'll share in the Google Classroom. I think if anyone has any doubts, I can discuss so that we can leave right now. So please share any doubts or something.